Welcome to the first in a series of videos on environmental aspects of Legionellosis outbreak investigations. Legionella bacteria commonly live in natural sources of fresh water, like rivers and lakes. However, Legionella only becomes a problem in man-made water systems, under conditions where amplification and aerosolization can occur. In order for there to be a risk for human disease, conditions must exist for Legionella growth, and there must be a method for aerosolization, which is the formation of small water droplets called aerosols. Transmission occurs when a susceptible host inhales the aerosols. The survival of Legionella in nature cannot be controlled, but with proper engineering design and maintenance, amplification, aerosolization, and transmission can be reduced. When one or several of these control measures fails, a Legionellosis outbreak may occur. In nature, Legionella grow and multiply within amoeba and ciliated protozoa, which are small one-celled organisms. Here you can see an amoeba packed with Legionella. In addition to providing nutrients for replicating and growing Legionella, protozoa also provide a shelter protecting Legionella from adverse environmental conditions, such as extreme temperatures and chemicals like chlorine. Human immune cells called alveolar macrophages look very similar to protozoa. When in human lungs, Legionella invade and grow within these alveolar macrophages and cause disease. In addition to growing in free-living protozoa, Legionella also thrive in communities of microorganisms called biofilms. Biofilms grow on moist surfaces and often look like dark slime. This slime is what shelters Legionella from harsh environmental conditions. Biofilms can be difficult to remove, even with scrubbing or using chemicals, and they may serve as a reservoir for persistent Legionella contamination that can last for decades. Biofilms may seed downstream devices and can come off in large chunks, which can result in transmission of Legionellosis. Legionella grow and amplify under certain conditions, including warm water temperatures, stagnation, presence of organic matter, and absence of residual disinfectants. Legionella prefers water temperatures between 77 and 108 degrees Fahrenheit. At temperatures below 77 degrees Fahrenheit, Legionella do not grow, but they also do not die. They are present and can amplify if more favorable conditions return. Legionella can survive in temperatures up to 158 degrees. Water stagnation is important because it promotes biofilm formation. The presence of organic matter like soil provides nutrients for growth, a stratum upon which to build biofilm, and also consumes free chlorine in the water. Disinfectants like chlorine or monochloramine kill Legionella and are typically added to potable and recreational water. However, these disinfectants can quickly break down under certain environmental conditions, such as high temperatures or increased organic matter. It is important to keep in mind that because of the protection provided to Legionella by protozoa and biofilms, Legionella can be present in water even if conditions are not optimal for their growth. For example, they may still be present and can cause infection in water that is hot and chlorinated. Legionella must be aerosolized to cause infection. Anything that produces small water droplets or mist, like a shower head, fountain, or whirlpool spa, can aerosolize water. Less commonly, Legionella can be transmitted via aspiration of drinking water, which is when water goes down the wrong pipe into the trachea and lungs instead of down the digestive tract. Now let's look at some common sources of Legionella exposure. Evaporative heat rejection equipment includes cooling towers, both open and closed circuit, and evaporative condensers. These are sometimes lumped together using the term cooling tower. Cooling towers use water to remove heat from a process or building. They are often part of the air conditioning systems of large buildings. In contrast, home AC units do not use water to cool, so they do not aerosolize water and are not a risk for Legionella growth. In an evaporative cooling tower, atmospheric air cools warm water by direct contact. During this process, some of the water evaporates into the air. Cooling towers typically use something called fill to achieve improved contact between the water and the cooling air. Warm water from a heat source, such as an air conditioner or industrial equipment, is pumped to the top of a cooling tower. The warm water flows down the fill, removing heat by evaporation. Large fans draw air through the fill, accelerating evaporation and further cooling the water. This generates aerosols. The cooled water continues to flow from the fill into the basin, then back to the heat source. Fresh water is introduced into the cooling tower through the makeup line to replenish what is lost through evaporation. Cooling towers can spread aerosolized water over a distance of several miles, but usually most of the drift falls downwind near the cooling tower. Drift eliminators are used in cooling towers to limit the escape of aerosols, reducing both water loss and the potential of Legionella exposure. Cooling towers create favorable conditions to grow and spread Legionella. For example, the water temperature of operating cooling towers generally ranges from 85 to 95 degrees Fahrenheit. Cooling towers can also accumulate airborne organic material that can serve as a nutrient source for Legionella. It is absolutely crucial for cooling towers to be properly maintained. A soup of chemicals should be added to the tower regularly to prevent growth of bacteria and algae. The water in the system becomes stagnant when cooling towers are intermittently used or are shut down, providing another favorable condition for Legionella growth. After being shut down, cooling towers can introduce Legionella into the air if they are restarted without following proper maintenance procedures. If the cooling tower water is contaminated with Legionella and the aerosolized particles are spread by the fans or wind, people can get infected by inhaling infectious droplets when they are walking or standing nearby. Moreover, if the cooling tower is located near the building's air intake or open windows, the contaminated air from the tower can get inside the building. Drinking water can come either from a public utility or from a private well. Public water quality is regulated by the U.S. Environmental Protection Agency, which requires a minimum amount of disinfectant to be present. This is called the residual disinfectant. The most commonly used drinking water disinfectants are chlorine and monochloramine. Private wells are subject to different rules and typically are not required to provide a residual disinfectant. Water usually enters a building via pipes in a maintenance room or basement. It is the responsibility of the building owner to maintain the quality of that water as it is heated, stored, and distributed through the premise plumbing to the points of use. The premise plumbing in a building includes all the pipes, devices, like water heaters, and fixtures, like faucets, that bring the water to the user. Water quality degrades as it travels through premise plumbing. The residual disinfectant supplied by the public utility is lost as it is consumed by organic matter or naturally off gases like bubbles in a carbonated soda. Heating the water further speeds up the loss of residual disinfectant. Hot water heaters come in all shapes and sizes, with different energy requirements, but share some common features. Hot water heaters with tanks frequently have layers of temperature, hotter near the heating element and cooler where cold water enters. Often, one or more layers are at the perfect temperature for Legionella to grow. Heated water may be stored in a secondary tank that could also have temperature differences within. Hot water heaters are most frequently powered by natural gas or electricity. Some solar-powered hot water heaters use the sun to directly heat water in pipes or tanks instead of through solar panels. This provides opportunities for growth because there are natural temperature variations when the sun is not shining. Cold water storage tanks are most frequently encountered in hospitals or other emergency centers that are required to keep a reserve of drinkable water. Residual disinfectant is lost when water is stored for long periods. Depending on climate, cold water can be warmed to temperatures that allow Legionella to grow. Hot water heaters and storage tanks often supply the optimal conditions that allow Legionella to thrive. In an attempt to prevent this, building owners use a variety of methods and devices, such as chlorine injectors, copper-silver ionizers, or filters. These interventions may be applied to any portion of the premise plumbing, but are most often installed on the hot water lines. There are two typical configurations for premise plumbing: recirculating and non-recirculating. A recirculating hot water system returns unused hot water to the heater. This is a common configuration in large buildings that reduces stagnation and lowers energy usage because less heating is required. Alternatively, systems that do not recirculate may have dead legs or areas of stagnation where water has a tendency to sit for long periods of time. These are ideal locations for Legionella to grow and then seed downstream areas of the water system. However, unused fixtures and devices may also be considered dead legs, so dead legs can still exist in recirculating systems. Hot water and cold water may travel through different pipes to the point of use. Thermostatic mixing valves blend the hot and cold water together to achieve a set temperature, reducing the chance of scalding. However, the valves themselves may become an area where Legionella can grow. Also, if the valve is located far from the point of use, for example right after the water heater, the blended water throughout the premise plumbing may be at optimal conditions for growth of Legionella. A spa, commonly called a whirlpool spa or hot tub, is a tub for recreational or therapeutic use. Spas should not be confused with jetted tubs that are drained and refilled after each use. Spas typically have the same system components as swimming pools, including a disinfection system, filter, pumps, motors, surface water skimmers, outlets and inlets, heaters, and piping. In addition, spas also have jets and air blowers that are designed to move water and generate bubbles, which create aerosols. Because spas are not drained after each use, the water in them constantly recirculates within the tub and through the piping and filter. A spa functions by skimming water off the surface and sending it through a filter where particles and contaminants are removed. The water then flows to a heater, where it is brought back up to temperature. Then disinfectant and other chemicals are automatically added to the water before it returns to the spa. Public spas should use an automatic mechanism called feeders to add disinfectant and chemicals to the spa. All the spa equipment, heater, filter, and chemical feeders, can be found in the spa equipment room. Spas that are not properly and consistently maintained can be sources for Legionella growth and transmission. The water temperature of spas, typically around 102 to 104 degrees Fahrenheit, is in the amplification zone for Legionella. Disinfectant residual is rapidly lost due to low water volumes combined with high temperatures and heavy bather loads. The jets in spas typically lead to aerosolization right at the water's surface. Careful attention to maintenance and cleaning is key to preventing Legionella growth in spas. Although persons using the spa are at greatest risk, it is common for people who are nearby and not using the spa to develop Legionellosis from inhaling contaminated aerosols. This is especially true for indoor spas. In many jurisdictions, the local health authority has regulations for the operation and maintenance of spas. Additional guidance can be found in the MAC, CDC's Model Aquatic Health Code. For example, the MAC recommends that public spas be maintained by a qualified operator and outlines detailed record-keeping requirements. A tip from the MAC: public spas should maintain a minimum free available chlorine concentration of 3 parts per million and a maximum of 10 parts per million. Thank you for watching. If you enjoyed this video, be sure to check out the rest of the series to learn more about investigating Legionellosis outbreaks.